Alright, this is video 7 for the rotation unit. So, we're going to continue talking about angular momentum. So the angular momentum of a system may change due to interactions with other objects or systems. So, for example, the angular momentum of a system with respect to an axis of rotation is the sum of the angular momenta with respect to that axis. Let's consider a system with particles in it. And all these particles are rotating around a center of axis, kind of like a solar system, if you will. We can consider all of those individual particles to be a system. And then the angular momentum of that system would just equal the sum of those three particles. And it doesn't have to be particles. We can think of all the individual atoms in a rotating object, and we can think of each atom as being like its own particle. So we could find the linear or the angular momentum of that object by looking at every single particle in that object. The next part here, the angular momentum of an object about some fixed axis, can be found by multiplying the momentum of the particle by the perpendicular distance from the axis to the line of motion of the object. So let's say we have an object or a particle that is going rotating around some axis. We can find the perpendicular distance, and because this is moving, we know that it has linear momentum. But what we could do is we could invoke V equals R times omega, the bridge equation between linear and rotation. And if we do, what we find is that the angular momentum equals the linear momentum cross the lever arm distance. We can find the direction of L with the right hand rule. So your fingers would point in the direction of P, of the momentum. So for us, it's coming out of the chalkboard here. Your thumb would point in the direction of R, and then the angular momentum then would be your palm, and that points straight down. So the angular momentum, the direction of the angular momentum here would be straight down. So to get the magnitude, what I could do is plug in mv for my linear momentum, and then I could plug in my V equals R times omega, so I'd have that, bring together the R's, then recognize that mr squared is the same formula for the moment of inertia of a particle. So I get my familiar equation right there for angular momentum, moment of inertia times angular velocity. Alternatively, the angular momentum of a system can be found from the product of the system's rotational inertia and its angular velocity. That's the one we've already been talking about. The change in angular momentum is given by the product of the average torque and the time interval during which the torque is exerted. So another way of finding angular momentum basically means that we can take the torque and time. That should make sense because we have the impulse momentum theorem. Where momentum equals a force times a time. So torque being the rotational equivalent of force, we could do that real easily. As far as units go, torque is a force times a lever arm distance. So the units, force is a kilogram meter per second squared. Lever arm distance is measured in meters. Time is measured in seconds. So this gives us a kilogram meters squared per second, which is the same as the units for angular momentum, because remember that for angular momentum, moment of inertia is a kilogram meters squared. Omega is a radian per second, but radian is unitless, so it's really a 1 per second. So a kilogram meters squared per second is the unit of angular momentum. If the net external torque exerted on the system is 0, the angular momentum of the system does not change. So, if the net torque on a system is 0, then the change in angular momentum will be 0 as well. The angular momentum of a system is determined by the locations and velocities of the objects that make up the system. The rotational inertia of an object or system depends upon the distribution of mass within that object or system. Changes in the radius of a system, or the distribution of the mass within the system, will result in changes in the system's rotational inertia. So, angular velocity and linear speed for any given angular momentum. And we're going to look at problems like this where we're changing either the mass of the system or the radius of the system to see what happens. All right, the last topic will be orbits. And I like to think of orbits going along with angular momentum. So, first things first, let's take a look at this, this system right here, this Moon-Earth system. And let's take a look at what's going on here. So there's only one force acting on the moon. That is a radial force. Consequently, the same strength force would also be acting on the Earth. But if I'm just studying the object moon, what I could do is I could take a look at the sum of forces acting on the moon, and I find that there's only one, the radial force. And since there's a radial force, it's going to be a mass times a radial acceleration. The distance from the core of the Earth to the core of the moon is called the orbital radius. I'll use a capital R for that. So that means then that this radial force, now what's providing this radial force is gravity. So it's a gravitational force, which equals mass. And if I'm interested in linear velocity, I'm going to use the v squared over r equation, where r is the orbital radius. The model for gravity, or gravitational force, be a mass of the moon, mass of the Earth, divided by the orbital radius squared. And now I can do some algebra. Mass of the moons would cancel. Take out one of those r's. So I would see then that the orbital velocity would equal that square root. So what this means then is that each orbital velocity has its own unique velocity, or speed at which the object must go. Or another way of looking at it is if an object is moving with some certain speed v, that will dictate what orbital radius it must have. So the further away from the Earth you get, as r becomes bigger, v becomes smaller, and it's definitely not a linear relationship because of that square root. But notice that as you get closer to the Earth, the object must travel faster to orbit. As you get farther away, the object can travel slower. So each velocity has its own discrete radius. Closer objects orbiting faster. We have different types of orbits. I'm just looking at 4. So I've got high Earth orbit, geostationary orbit, medium Earth orbit, and low Earth orbit. So let's take a look at each of these. I'm going to use capital O r for orbital radius. So for high Earth, the orbital radius is somewhere greater than 26,000 miles. The orbital period is how much time it takes to make one complete path around the Earth. So for high Earth orbit, the orbital period is greater than 24 hours. And an example of a satellite it's a TBEX, it's a satellite, and it has an orbital period of 216 hours. Another example of high Earth orbit would be the Moon. It has an orbital period of 1 month. Geostationary orbit is an orbital radius that is equal to 26,199. Now, geostationary means that it stays at one position above the Earth's surface. So the orbital period equals 24 hours. So because this satellite takes 24 hours to go around the Earth, and the Earth makes one rotation in 24 hours, that means the satellite will stay at one position above the Earth's surface. And some examples for this will be communication satellites. It should also be noted that because the Earth is a sphere, these satellites tend to be over the equator. So if you have Dish Network or DirecTV or some other satellite-based television, you'll notice that your satellite in your front yard or backyard, whatever, points to the south. That's because we live in the northern hemisphere, and the equator is to the south of us. So when they point that satellite to the south, what they're doing is pointing it towards a geostationary satellite. Medium Earth. This orbital radius is in the neighborhood of 12,000 miles. So the orbital period, I'll go OP for orbital period, is right around 12 hours, so about half a day. Some examples of this are the GPS satellites, global positioning satellites, or global positioning system of satellites. Low Earth orbit. The orbital radius is right around 1,200 miles. The orbital period is right around 2 hours. So about 120 minutes. So some examples of these will be spy satellites. Also, the International Space Station. It should be noted that spy satellites then, as they're flying over, only have about 2 to 3 minutes before they cross the horizon. So they only have about 2 to 3 minutes to take pictures of an installation. And just from the physics of optics, they cannot, it's not like you can use a spy satellite to read someone's license plate or even look at an individual person. Honestly, they're only good at counting maybe tanks or buildings. That's about all they're good for. So it's not like it is in the movies. All right, so going on with orbits, we have an important name, Kepler, and Kepler created 3 laws for orbiting satellites. The first law is that planets travel in an elliptical orbit, so makes pretty good sense. The star or the sun would be at the focus of one of the foci of that ellipse. Even though there are ellipses, Earth's orbital path, it's elliptical, but it's still pretty close to a circle. Same thing with the moon. It's an ellipse, but it's pretty close to a perfect circle. The second law is that a line drawn from a planet to the sun sweeps out equal areas in equal time intervals. So, for example, here I have, let's say, area A1, and notice that this takes 1 month. If I have an area right here, I'll call this A2, this is still 1 month. Well, if I were to find those areas, I would see that they're the same. And that's true for all areas that sweep out 1 month. So this area and this area is the same. This area and this area is the same. So that's Kepler's second law. The third one is that the square of the orbital period is proportional to the cube of the average distance from the planet to the sun, or the orbital distance. Okay, so for this one, if we go back to the very top of this page, we saw that this relationship right here. Okay, so if you need to go back to the top of this page and look at that math real quick just to check this out. So I've already derived this. Okay, now, as a planet goes around its star, or as the moon goes around the Earth or whatever, it travels at a constant speed. So when I do my kinematics, the acceleration is 0, it's gone. So in other words, the velocity would be, displacement over time. Well, if we think about something going in a circle, its displacement is circumference. And the time it takes is the orbital period. So the velocity, if we think about that, circumference is 2 pi times the orbital radius, and all that divided by the period. So we can plug that into our equation up here. All right. Now I can do a little bit of math. And I'm going to cross multiply to turn this into a linear equation. And then I'm going to go ahead and solve this for period. So for pi squared, g, mass of the Earth, those are all constants, so those kind of get grouped together. And I want you to see then that the orbital period squared is proportional to the cube of the orbital radius, which is the average distance between the planet and whatever's orbiting around it. Now I put mass of the Earth, but I could have mass of the Sun. I could have mass of Jupiter. You know, it's whatever is getting orbited around. All right, it's going to conclude our notes on the rotation unit.